All right, I wanted to talk about a few things to hopefully help you with your work today. And so I'm wrapping up the describing velocity packet and also the reading. So the first thing that I want to do is to be sure that you understood the definition of displacement, and it means a change in position. So this is from the reading on displacement. And the formula for it, so the symbol is delta x, or that's if you're in the horizontal position, or delta y if you are in the vertical position. And the formula for it is the final position minus the initial position, where the sign of x and y makes, or of x final makes a difference. The sign of the positions matters. The unit is typically the meter, but you could also be in centimeters or millimeters or kilometers. So let's do an example from the book. This is actually from your reading. Hopefully you were able to successfully figure this out, but if not, I wanted to talk to you about it. So I want to figure out the displacement between times 1 second and 3 seconds. And the way you might think about notating that is that you would do, this is the displacement from 1 to 3. And so this is going to be the position at 3 seconds minus the position at 1 second. All right, so at 3 seconds, we're right here. So this is x final. And at 1 second, we are right here. So this is x initial. I know that's not x0. We're talking about our initial position is at 1 second. And so my final position is at 45. And so we're going to subtract our initial position, which is 150 meters, and that gives us minus 105 meters. Now, this minus sign is just telling us the direction. This is the direction, whereas this is a mathematical function. So it means subtract. So we use minus signs in two ways in physics. That's one of the things that can be a little bit difficult, is that sometimes we use the negative sign for direction, like the answer, and sometimes we actually mean the mathematical function to subtract. So what does this mean from a real standpoint? So we can see that as we look at the scale, that to the right is positive because the numbers are increasing. And so negative means to the left. And so it's just telling us our displacement, oops, to have an actual thing, our displacement vector looks like this. So it is to the left, and it is 105 meters long. All right, so that is displacement. Final position minus initial position. Okay, true or false? The length of the arrow used to represent the velocity is proportional to the speed. And that would be true. Okay, so when you are drawing vectors, if you have one velocity, I'm just making these numbers up, is 2 meters per second. And then another velocity is negative 4 meters per second. What they should look like is, that would be our 2 meters per second. And then the other one I want to make twice as long. Let's see if I can do that. That's about twice as long. And I'm doing the negative because negative to the left in this case. Twice as long to the left. So that's what your vectors should look like. All right, so this was a question from the reflection on 008. So of position, displacement, and velocity, which quantities stay the same when the origin is moved? So in order to do this, I'm going to choose 2 points in space. I'm going to choose an x initial and an x final, and they have to occur at the same point in space. And I'm going to give those in pink. I'm going to sneeze, I'm sorry. Excuse me. So I'm going to say that this is my x initial. I'm putting it on two different number lines, but they're going to be the same point in space. And then this will be my x final. So x initial and x final. So, and I'm putting them on two different number lines, but we're going to say that these are the same point in space. I know that they are above each other, and that's just so you can see mathematically what I'm doing. So when I take the number line and slide it one position to the left, I can see that the position changes because when I have the number line here, x final is 3, x initial is -2. When I have the number line here, x final is 4 and x initial is -1. So the choice of where I put the number line makes a difference on position. So we're going to cross that one out. Okay, now let's look at displacement. So on the top number line, I know my displacement is equal to x final minus x initial. So this is going to be 3, because this is x final on the top minus, and then x initial is -2, and so that's going to give me a displacement of 5. On the bottom number line, delta x is x final minus x initial. And so here my x final is 4, and then minus my next x initial is -1, and so that is equal to 5. So in both cases, my displacement is 5. And so changing the number line has not changed displacement. So this stays the same. Now, velocity is just displacement divided by time. And time doesn't change with my, where I put my origin. And so velocity is also going to be the same since displacement is the same. Okay. Distinguishing between graphs of position and graphs of velocity. So this is from 009. Now, when I look at a position versus time graph, so this is where I have x versus t, how do I tell which direction the object is moving? Do I look at the slope? The sign of the slope tells you the direction of the motion. Or do I look at the values of the function? The sign of the function tells you the direction of the motion. All right, so for position versus time, I actually look at the slope, and the slope tells me the direction of the motion. So I have a graph of position versus time, and the slope of this line, negative slope, so this means negative direction. Over here, I've got a positive slope, and so this tells me that I'm moving in a positive direction. Now, for velocity versus time, I actually look at the values because this represents +1 centimeter per second. This one is +3 centimeters per second. And that plus sign tells me the direction. So this is one case where the sign tells me the direction. Whereas I look at here, this tells me -1 centimeter per second. And this negative sign, this tells me the direction of motion is negative. So when I'm looking at velocity versus time, everything above the axis, everything above the axis is positive motion, or I'm moving in the positive direction. Everything below the axis, that's not going to show up. Everything below the axis is negative direction. So you're going to have to, it's important to distinguish or note whether you're looking at position versus time, in which the slope tells you direction, or velocity versus time, in which the sign of the function tells you the direction. All right, so I thought to help you that it might, like position versus time, I thought that we might try matching velocity graphs with these graphs right here. And I think that that might help you figure out the difference between the shape of the curve of a velocity versus time graph versus a position versus time graph for the exact same motion. All right, in case you have forgotten how to do it, you're going to grab one of the sensors from the side. They should all be charged. And you will open SparkView. So remember, this is SparkView, and it's the app that is kind of blue, and it's got a couple of white circles, SparkView. You're going to go to the three lines at the top left, and you're going to start a new experiment, and then choose the sensor data. And then you will connect your sensor, make sure it's your sensor. But instead of choosing position, we want to uncheck position, and we want to check velocity, and then we want to choose a graph. So that's going to give us graphs of velocity versus time. And remember that you can change your origin with the zero sensor now, and you can change the sign in terms of whether heading towards the sensor is positive or negative motion. The one thing I'll remind you is that we already had a discussion about how changing the origin might affect displacement or velocity or position. So you will have to decide whether or not it matters if you actually change the origin. So go ahead and see if you can graph match these. I'll just tell you this one's going to be hard to do because that sudden jump is idealistic. And so if you get kind of a sigmoid curve like that, that's doing pretty good. So, all right, go to it.